I see you. Yeah, perfect. Hi, everyone. My name is Eleni. I'm a PhD student at Princeton University under the supervision of Professor Mitterberger, and we are the XIA Lab. I'm going to present a research project that we did using COMPAS XR. And before diving into that, I will just um, say a few words about what COMPAS XR is, to help humans to assist with the shortcomings of robotic fabrication while remaining the advantages of robotic computational design. We developed COMPAS XR, leading to an adaptive digital fabrication and human-machine cooperative fabrication processes. In very few words, the main components of COMPAS XR are three. First of all, we have the COMPAS XR Python library with CAD integration, cloud services in between, and then COMPAS XR Shark library that can be used to develop user-facing application for different devices, such as phones. And the cloud services allow to link multiple clients, multiple phones, let's say, together. While in this presentation, the project that I'm going to talk about does a step towards the COMPAS XR HMD for head-mounted displays devices. COMPAS XR so far has been used in many projects. Some of them, I think, have been already presented in these sessions. So I'm gonna talk about the last one, the Daphne scheme. That it's a project by Mate, and it's exhibited in Milano Triennale until end of November. I'm gonna say a few more things about it. Daphne scheme defines architecture as a living ecological system transformed through dynamic interaction between machines, microbes, materials, and humans. It contrasts the traditional building system because it views architectural envelope as organic interfaces. It is a canopy covered with hand split large shingles, which provide a breeding ground for bacteria and microalgae. Regarding the actual fabrication of the installation, an augmented reality workflow was developed to improve the design and single link process with an unknown material stock. And the shingles that we got and they were meant to cover the steel mesh were split by hand, resulting in various widths between 5 to 16 centimeters. The exact geometries of the individual shingles were unknown until then built up on site. Therefore, a fast design and fabrication logic had to be set up that allowed us to recompute the design based on the available material. So first we had a workflow to create a digital inventory out of the materials that we received, and then to adapt the design that we had before going to the site. And in the end, an application for assembling the pavilion with two teams and instructions through head-mounted displays was developed. Regarding the software architecture behind this workflow, for the creation of the digital inventory, we had the scanning station and then a correction app that the operator had and could correct any errors during the scanning. And in the design, we use the familiar like Rhino and Grasshopper workflow, and for the AR assembly, Unity packages, the OpenXR for localization, and VMRTK, which is specifically for HoloLens. All of these three phases were linked together through COMPAS XR and the functionalities that it offers through the Python library and the Sharp Unity. More specifically, since this project didn't have human-robot collaboration, and it was only for instructions for human operators, the main functionalities that we use from COMPAS XR had to do with the user interface and the communication between the CAD environment and the AR environment through Firebase and MQTT. As mentioned, we, for registering the individual elements, we didn't care for the specific dimensions, although we were able to get them. And we were more interested to categorize them so that we can easily distribute them in the design later. So we actually created 4 different categories, and then using this scanning station that I mentioned before in the AR application, we started scanning them one by one and putting them in the correct category. The interface of this application was very simple in order to make sure that it will not create extra fatigue to the person that was using it and had only the necessary information. And we used color coding for the categories so that can easily match the information that they could see, like the stickers that we placed on site with the information that you had on hand. And of course, the algorithm that we used could lead to some wrong registrations. For example, when there was like a big, like a very sharp shadow next to an element, or there was a groove in the piece. So the operator could just easily change the dimensions of the element and place it in the correct category when errors occurred. We managed to, with this workflow, to scan around 2025 elements, individual elements, and for every registration that we did, like with every item that we were saving on the Firebase, we weren't saving only the category that it exists, but also like more information so that we know how often we had to fix to change the category and how fast this was proceed, and of course like who was the person who did it, in order, like in case we have some errors or not, to keep track of the whole workflow. And after that, it was very streamlined, to be honest, to change the design, to adjust actually the design on site in a very quick way. We had to, so the algorithm that we used for the placement was positioning the available elements from the inventory along contours based on local curvature and surface orientation. It adaptively determines placement gaps based on local geometric properties such as curvature and concavity, optimizing the alignment of the singles and overlap while respecting physical and, let's say, aesthetic constraints. This design was then described as a COMPAS assembly, and in the attributes of its part, we decided to save an arrow shape for using it later for the instructions, and the category of the element that was used later to make sure that the correct coloring of the elements will happen in the visualization of the app. Regarding the interface of the AR assembly, we based we used all the functionalities that the COMPAS XR for mobile devices offers, and then we just adjusted in a minimal hand menu from MRTK, which is with locks in place when we move the hand down, and then we hide some other, so the basic functionalities of like moving to the next elements and say them as already built or not, were in the main menu, and then we had some other extra menus about visualization in the More button, and some extra functionalities regarding the localization. The extra functionalities that we just see here is 2 buttons, the move and rotate. It gave the freedom to the user to adjust a bit the overall AR visualization on space, because it was an active construction site, let's say, the installation place. So a small mismatch with the QR codes could lead like in a very wrong visualization. So the user could actually like rotate a bit the structure or move it in space to make sure it matches the actual steel structure on site. And this is how what an operator was seeing every while assembling. It's pretty much similar. It's exactly the same logic as the COMPAS XR for phones. You could see which is your item that you need to assembly and like your little indicator, and then where the other person that it's assembling is, and the different in which type of element you need to place and where approximately. Since we weren't like we weren't aiming for like accuracy of millimeter. And then the structure was assembled with 2 people working at the same time, and accessing a shell cloud-based model. This ensured that all teams work for the same up-to-date information, reducing distraction errors by clearly communicating the required assembly steps and sequences. And it was free to the operators to define their own sequence of placing things. Let's say we didn't have the priorities set by layer because we realized that there are a lot of parameters that affect this. For example, if we had a ladder at the moment and we could build up on one side or not, a lot of problems that they come up with the actual construction of elements, and we want to address the next projects and developments of COMPAS XR. As mentioned in the beginning, the installation is part of the 24th International Exhibition in Milano Triennale, and you can visit it until November 9th. You can also visit our website, Daphne's Skin, if you want to learn more. I would like to thank all the members of the team that made this project happen. And of course, thank all of you for your time and for the opportunity to talk about this project here. Thank you.